Well, hello again. This is an example of an application of the standard deviation. The last video, I tried to motivate a little bit the purpose or a need for a measure of dispersion through that airplane drop example that we looked at, measuring the tightness of a data set, the dispersion or the variability of a data set. Hopefully now you're comfortable with computing the standard deviation, the variance, and even the range. But what we want to look at here is a further application of this measure of dispersion. In particular, we're going to look at the application of the standard deviation. This accompanies the last lesson in Chapter 4, or Chapter 4 of the Hawkes material. And there's basically two applications that we're going to look at here through this example. And what I want us to look at is, suppose that we have this variable. I'm going to call it x, but x stands for the value of the stock of Ford, and it's got a mean of 20 and a variance of 16. So suppose from this data set we've got those two values. And I want to assume that those values are parameters. That this is the population data set here. So mu would be 20 and the variance would be 16. And this makes sense that the value of a stock has a variance. What's saying on the average, this is the value of it. Say, oh, let me back up. I need to say, suppose these numbers are for a 6-month period for Ford. And during that 6-month period, the value of the stock goes up and down, but the average of those values is 20, and the variance of those values is 16. This reflects the variability in the values of Ford stock. And this represents the location or the center of the values of Ford stock for that 6-month period. Now, these values 20 and 16, I made them up. Those aren't any real values there. Okay, so the first question, let me back up. So sigma squared is 16, so that implies that the standard deviation would have to be 4, right? The square root of 16 there. Okay. First question here, what can we say about the proportion of x values that are between 12 and 28? And what result would we use to establish such a proportion? So this might be of interest here. Are many of the x values between $12 and $28? Maybe that's an important range for a stockholder or for someone interested in buying this stock or selling this stock. So I'm going to draw a number line here to help us get a sense of what's going on. Here is 20. I'm going to bump out one standard deviation to the right, which would be 24, right? If mu is 20, then mu plus 1 sigma would be 24, because sigma is 4 here. Okay, I'm going to bump out another standard deviation to the right, and that would be 28. And this would actually be mu plus 2 sigma. I'm going to bump out a third standard deviation to the right. That would be 32, and this value would be mu plus 3 sigma. I'm going to do a similar thing to the left here of the mean. One standard deviation to the left of mu would be 16. So here I'd have mu minus 1 sigma. And another standard deviation to the left would be 12. This would be mu minus 2 sigma. And then over here, down to 8, that's another standard deviation, mu minus 3 sigma. So I hope you have a sense of what's going on here. I've partitioned the x, the values of x on this number line according to the standard deviations away from the mean. So when we look at, when it says the proportion of x values that are between 12 and 28, we're actually looking at this range right here. between 12 and 28 there. And that is actually, when we think of 12, between 12 and 28, those are the x values. These are the x values that are within 2 standard deviations of the mean. That within means to the left and the right, 2 standard deviations of the mean there. So what we want to know is, based on what mu is and what sigma is, what proportion actually lie in this range. Well, in terms of applying the standard deviation, we only have one result that will help us here, and that's Chebyshev's theorem. And I'm assuming that you've read over and studied and perhaps even worked through a problem or two with Chebyshev's theorem. But Chebyshev's theorem basically says that the proportion of x values that are within k standard deviations of the mean is greater than or equal to 1 minus 1 over k squared. So that ought to be familiar to you. That quantity there, 1 over greater than or equal to 1 over 1 minus k squared. So when I look at the problem set up here, when I look at the window 12 to 28, that these x values are within 2 standard deviations of the mean. And so for this problem, so by Chebyshev's theorem, by the way, Chebyshev was a Russian mathematician who did a lot of work in probability theory, which we'll get to later in the course. But by Chebyshev's theorem, the proportion of data that is between 12 and 28 is, that proportion is at least 1 minus 1 over k squared, which is 1 minus 1 over k. What's k? K is the number of standard deviations that you're within the mean here. So k here is 2 because we're within 2 standard deviations of the mean here. This is k. Okay, so this is 1 over 1 minus 2 squared. 1 minus 1/4, 3, that's 3/4, or 0.75. So Chebyshev's theorem says that the proportion of data that's between 12 and 28 is at least, now that's an important idea, it's at least 0.75. So it's 75% of the data or more is between $12 and $28. Okay. Now, what if we can be a little more stringent about what we know about this data set? Let's add a condition to it. Suppose that we have a histogram, which I've seen before, or some other means that tells us that the distribution of this data is mound-shaped. If we got that information, what further can we say about the proportion of x values that are between 6 and 24? I'm sorry, $16 and $24. What proportion of stock values are between $16 and $24? That's basically the question here. And what result would we use to get such an answer? Again, I'm going to draw a number line here representing x. I've got 20 in the middle, and I'm going to go out to 24. Again, this is a bit redundant. Then out to 28. To the left, 16. And to the left, even more, 12. Here again, this is mu. This is mu plus 1 sigma. This is mu plus 2 sigma. 16 is mu minus 1 sigma. 12 is mu minus 2 sigma. So when I think about this, the x values between 16 and 24, I'm looking at this range right there, and that range describes the x values that are within one standard deviation of the mean, right? One standard deviation to the left and one standard deviation to the right. So within 1 sigma of mu. That's how we think of that. So how can we handle this? Well, we could use Chebyshev's theorem again and say, well, that proportion is at least 1 minus 1 over k squared. In this context, k would be 1. So we'd have 1 minus 1 over 1 squared. So that would give us 1 minus 1, or 0. So it's saying the proportion is at least 0. Well, that's really not very informative. But if we use this other result that hopefully you've read about, we can use the empirical rule that has the condition of a mound-shaped distribution. If our data is mound-shaped, the empirical rule gives us approximate proportions approximate proportions of data lying in certain ranges. And so you've seen that in your text or in the Hawk software. But by the empirical rule here, what we're going to apply by the empirical rule, the proportion of data that is between 16 and 24 is approximately 0.68. And the reason it's 0.68 is because we're within 1 sigma of mu. If you've seen the table involving the empirical rule, within 1 sigma, the proportion of data is 68% is within 1 sigma of mu. 95% of the data is within 2 sigma of mu, and nearly, I'm sorry, let me back up, 0.997 is what your text has. 99.7% of the data is between 3 sigma of mu. And so if we just think about what this says, is that when you're within 2 data values that are within 2 standard deviations of the mean, excuse me, are pretty likely we're going to observe that. But data values that are outside of 3 standard deviations of the mean, you're not going to see a whole lot, because most of the data is within 3 standard deviations of the mean, at least when the distribution is mound-shaped. Okay. Some differences here between what we got in 1 and 2. This is 0.68, but it's also, our answer is approximately 0.68. And here we have 0.75, but it's at least, and because that's how Chebyshev's theorem is worded in terms of at least. So there you go. Not only can you compute sigma, but sigma can be used to answer these kinds of questions. The proportional amounts that data are within certain intervals of the mean here. Okay, well, I hope that this was helpful.